Hi there, Turgeon here, bringing you physics from afar. This is cash. This is a cash bid. So, is antique property of an old monetary system before there was Venmo, and we had these things called cash registers before credit cards. I'm willing to bet $20 on various items that they will be on the AP exam, the AP physics exam. 15-minute time limit. Let's go. This is designed to be complementary, not necessarily comprehensive. We're calling this main topics, and I'm putting a lot of emphasis on certain things. If I look at the equation sheet, it makes me think of kinematics when you look at this first section here, and we can translate those into different forms. For example, as soon as I see that equation, I want to rewrite it as the definition of acceleration that you're more familiar with. This makes me think of a very specific strategy where we list the variables. There's an exclamation point here, listing the variables. So if I write A equals, D equals, T equals, this is the money strategy for kinematics. It's also the money strategy for projectiles. And remember, if you have a projectile problem, even if you're just working out a conceptual problem, remember, list the two quantities separately, even if it's a conceptual question. So horizontal, vertical, you might as well just write D, V, and T in the horizontal. And you can write that you can always write the accelerations -10 for the vertical. You should pay attention, because if it's a horizontal launch, for example, initial velocity is going to be 0, possibly. But projectile diagram, here we go. I'm on the clock, can't make this too long. Let's see how long it takes to draw a semi-decent projectile diagram. Horizontal components always the same, never stops even at the peak. Oh yeah, there you go. You can see that the horizontal are the same. The vertical changes because it's undergoing a constant acceleration due to gravity. The main idea here, though, is you're listing your variables, you're listing them separately if it's a projectile. This also makes me think of slopes and areas and graphs. Check this out. You got your position graphs, which is often shown as an X and a T instead of D, but you might see that as D. Then you have, of course, velocity graphs over time. The velocity graphs, I should extend into the negatives there. So position graph, here's 3 classics. This would be increasing velocity because the slope's increasing. This would be decreasing velocity. This would be constant velocity right up the middle. This has 0 acceleration. This is a negative acceleration. This has a positive acceleration. It's in the slope is the velocity. Position over time, meters over seconds. The velocity graph, I'm going to make 2. Let's call this graph A, and let's call this other one graph B. And let's just say out loud what these two things are doing. These are supposed to be horizontal lines. So for graph A, during this first segment, the object is increasing its velocity, then it's constant velocity, then it's decreasing its velocity, but these are forward the whole time, forward. And down here in segment B, this is increasing velocity, but in the negative direction, speeding up. This is constant velocity, but in the negative direction, that's going backwards. This is decreasing velocity, but in the negative direction, so it's slowing down. Dynamics. When I think dynamics, you basically think Newton's second law. And when you look at the equation sheet, there it is. I see that F net, and that F net reminds me to draw forces. Okay, let's do the basic 4 forces, and then we could just always modify those. The basic 4 forces, these are going to be wrong in a lot of situations, so that's crazy. Why would I draw those? Because they give you somewhere to start, and you can think, is that really there? Is that really there? Is that really there? This might be an applied force or something. But now I have a place to start. Like, oh, is this an elevator? Oh, there's no left or right action, right? If that's an elevator. And then if it's an elevator, maybe it's accelerating up and down, up or down, and the normal force might be greater or less than the weight. If this is hanging by a cable, then that's not going to be normal force. Maybe it's going to be tension, but it's a way to start. If there's an angled force, then maybe this is up an angle. Now I got to think about components. Maybe this becomes a component, then maybe that changes the normal force. But the idea is if you start with those four forces, you can just kind of modify. Also reminds you that you have to consider this question, the normal force and the weight. Are they equal? They may or may not be equal. Inclines. Force on an incline, remember this? Draw the weight straight down. Weight is always straight down. Draw the components parallel and perpendicular to the incline. And remember, the normal force is normal, which means perpendicular. And the normal force will equal that vertical component of the weight. It does not equal the weight. In circular motion, I'm prompted by this thing. I mean, I feel like you could say stuff about friction. Basically, the equation says it all. The equation tells you about the relationship between friction and normal force. But check out this equation about circular motion. Centripetal force, oh yeah, the centripetal force is related to the net force. So F net is ma if you rearrange. So F net is m times centripetal force v squared over r. That came right off the equation sheet, basically. And now I got to think about situations such as a roller coaster at the top. Maybe I have the weight of something going down and I have a normal force going down. And then if I have a roller coaster at the bottom, I still have the same weight going down, but I'm going to have a different normal force going up because I always need a net force toward the center. Net force toward the center. Then we see in gravitation. I'm jumping to gravitation. So I see this equation and I see this equation below it. For these two. Now I see, oh, this is reminding me that I've got gravitational acceleration. Okay, so if you look at the gravitational acceleration, that's local gravity. G is equal to the gravitational force. This means it's a vector. That's gravitational field or acceleration due to gravity. And if I just write the expression gmm over r squared, all divided by m. I did a capital M to represent the planet. You see how the gravitational acceleration on a planet is gm over r squared. Now, I would bet $20 that somewhere on the exam you're going to see some situation where you had to draw those forces. Somewhere in the exam you're going to see these graphs where you had to know those relationships. Somewhere on the exam, you're going to see an incline and you have to be aware of those forces. And I'm going to bet $20 that somewhere on the incline, they're going to ask you something, somewhere on the incline, somewhere in the AP exam, they're going to ask something, oh, well, what happens if you double the mass of the planet, but then you triple the radius? Well, if I triple the radius, I divided the gravitational field by 9, and then I doubled the mass. So now that means that the gravitational field is going to change by a factor of 2/9. Okay? That's reasoning with equations. Write the equation down and then look at the equation. Okay? Work kinetic energy theorem. Energy is a go-to. Always think energy first. Work kinetic energy theorem is FD equals 1/2 mv squared. But remember, that's the change in the kinetic energy. And how am I supposed to know that? Well, that's related to work. Work, you've got your parallel force. Remember, that's the horizontal components. That's why we have the cosine of theta. And there's work being related to that. Remember that in FD graph, I'm thinking area. Could look like anything, right? But I'm thinking the area of that FD graph. Now, I can guarantee master equation somewhere, $20 plus the work done. Let's not worry about rotation yet. And then there may or may not be a 1/2 kx squared as well. And then we're going to have another mgh and another 1/2 mv squared. This is the master equation. If you write it out, you can then cross stuff out. I could just put a little sub 2, little sub 2, little sub 2 right there. Master equation, energy conservation, best way to think. Now remember, isolated system versus external forces, like those weirdly defined situations such as the one you saw on your practice exam. The external forces would mean that you have a system that you're saying this object's not part of it, and then anything it does is an external force, so it's going to add to the system or take away from the system. That means you don't have energy conservation anymore. Energy conservation assumes an isolated system. Momentum, remember, collisions. Remember, the center of mass during a collision has a constant velocity. And I'm not going to go over too much how to find the center of mass. You got to use some intuition there and look at previous examples. But remember, the master equation, you're going to use it. And it may or may not be elastic. Remember the impulse momentum theorem? Here's impulse. That results in a change in momentum. And if I have a graph, could look like anything, could look like this. If it's force and time, I'm thinking area. And that area is going to literally be the change in momentum. That area, you can compute it, or maybe they tell you what it is. That area is going to be the change in the momentum. Rotation. Remember, conservation of angular momentum, if it's isolated, that means you have I omega equals I omega if that's a situation such as the skater pulling their arms in, where you are keeping the you are keeping all of the mass in the system, but maybe you're changing the moment of inertia. But honestly, more frequently on the AP exam, it's more this concept, and they want you to say, they want you to choose an answer choice that says L total is constant and unchanging. They want you to recognize that you're probably going to say that somewhere. I might only bet $10 on that, but you're probably going to say something. They want you to recognize, oh, like a planet orbiting a sun. Hello, the angular momentum of this system is constant. It's isolated. It's just the planet and it's the sun. It's orbiting around it. Now remember, torque. The definition is in the computation. You've got a parallel force times a distance from the pivot. And you got stuff like this, like maybe there's your pivot point, and then we have a downward force over here, and then we have another downward force over here, which has to be less because it's further away from the pivot. And you can see that we have equilibrium in both directions. They're gonna want you to say, see how we have the counterpart here for F net, but the counterpart would be that alpha is equal to the torque net, not divided by the mass, but divided by the moment of inertia. They want you to say somewhere, instead of saying like, oh, the thing accelerates in an angular sense, they want you to say there's a change in angular momentum. I don't know why, but they really like to do that. They really like to, instead of saying it accelerates rotationally, they want you to say there is a change in angular momentum. They like that. Notice that. What else? There's some stuff. For when we say timing, I mean saying something like t is 2 pi root m over k. And they want you to understand these relationships between mass and spring constant. This is like a finicky topic. I don't know how much to bank on whether or not you're going to see this specifically. I think something in this category, though, of understanding the oscillator, but it's not a super heavy topic. Simple harmonic oscillators are kind of touch and go and not as reliable as the rest. If you take a look at the equation sheet, you'll notice I kept referring back to this. Use these as anchors for the various hints I was giving you. And remember, write the equations down. You can look at them and they serve as a basis for your reasoning. Comprehensive? Not necessarily. Complementary? I hope so. This has been Physics from Afar.